Welcome to the Explainer. Today, we're diving into the fundamental speed limits of modern computing. Specifically, we're talking about heat and bandwidth. To solve a really looming crisis in high-performance technology, engineers aren't just trying to build better wires anymore. Instead, they are fundamentally rewriting the rules of communication by shifting away from electrons and moving toward photons. Think about it. For decades now, our processors have just been getting exponentially faster. But the traditional electrical wires connecting all those processors, they've actually become a severe bottleneck. As our data demands completely skyrocket for things like artificial intelligence and massive digital workloads, pushing electrons through standard copper just generates way too much heat. It consumes massive amounts of power, and it literally physically limits our data transfer. Electrons simply aren't fast enough anymore. So how exactly do we break this bottleneck? Let's get into Section 1, Defining Silicon Photonics, a light speed evolution. The solution to our bottleneck is something called Silicon Photonics, or SI for short. This is a platform that uses standard semiconductor manufacturing processes, but instead of making electrical paths, it builds microscopic optical components out of silicon. Now, you might be wondering why silicon? Well, believe it or not, silicon is actually transparent to infrared light, so engineers can literally carve microscopic pathways right onto a silicon wafer. By surrounding these pathways with materials that bounce the light back inward, they create a perfect little channel where light can travel at absolutely astonishing speeds with incredibly little loss of energy. Now, this idea didn't just pop up overnight. Back in the 1980s, researchers first proposed what was, at the time, a totally radical idea, placing optical circuits and electronic circuits together on the exact same chip. For a few decades, that was really just a theory. But a massive turning point hit in 2005 with the development of the silicon modulator. Basically, our fabrication processes finally caught up, allowing lines to be drawn thin enough to actually guide light. Fast forward to today, and that single breakthrough is enabling devices to operate at blistering speeds that easily exceed 100 gigabits per second. Moving on to Section 2, Circuitry for Photons, or what we can think of as wires of light. So why go through all this trouble to use light instead of our trusty old electrons? Well, it really just comes down to physics. Traditional electrical interconnects suffer from lower frequency bandwidth, and they lose a lot of energy because they generate heat. Optical interconnects, on the other hand, operate at vastly higher frequencies, which unlocks just massive amounts of bandwidth. And because they are microscopic and generate virtually no friction, they consume far, far less power. It's really a win-win. To actually make this optical magic happen, engineers rely on a few absolutely crucial components. First, think of waveguides as the physical wires guiding the light around the chip. But light all by itself isn't data. It needs to be encoded. That's where optical modulators come in. They act almost like high-speed shutters, constantly changing the light's properties to embed our information. Then we have microscopic lasers that generate this light to begin with. Though interestingly enough, these lasers are usually made from exotic compound materials, not silicon. And finally, at the end of the line, receivers use photodetectors to catch those photons and translate them right back into a standard electrical signal. Let's put the whole shebang together. Think of it like a seamless, lightning-fast relay race. Step 1, traditional integrated circuits deliver an electrical signal. Step 2, our semiconductor lasers fire up, and the optical modulators instantly encode that incoming data into a beam of light. Step 3, those perfectly encoded photons speed through microscopic waveguides with almost zero energy loss. And finally, Step 4, the receivers catch that light and instantly translate it back into electricity. It goes from electricity to light and right back again. All right, Section 3, the CMOS advantage, which means we are mass production ready. You know, the real game-changing advantage of silicon photonics actually isn't just its speed, it's scalability. This tech is able to utilize existing CMOS manufacturing techniques. CMOS stands for complementary metal oxide semiconductor. Now, the global semiconductor industry already produces over 1 trillion chips every single year. Because silicon photonics is, well, built on silicon, companies can leverage the exact same multi-billion-dollar factories and fabrication tools they already use for traditional computer hardware. They don't have to reinvent the assembly line. And the global supply chain is already mobilizing around this. Many of the major semiconductor foundries are laying down strict standards for photonic integration designs. By standardizing the blueprints, so to speak, foundries are making it incredibly efficient, fast, and far less expensive for new companies to jump into the photonics market. It's paving the way for incredibly robust new product development. Of course, it isn't all perfectly smooth sailing. Let's look at Section 4,
Challenges to overcome in physics and fabrication.
Despite all this amazing momentum, we have to be real. Some significant hurdles still exist. First up, silicon fundamentally limits the frequency of light you can use. To get around this, researchers are having to blend in new materials, like silicon nitride, to broaden the range. Second, as I mentioned earlier, silicon cannot natively emit light to create those tiny lasers. So the industry is currently fighting to integrate exotic 3V materials, stuff like indium phosphide or gallium arsenide, directly into the manufacturing workflow. And finally, there's the cost. To make this economically viable for everyone, production absolutely has to scale from millions of chips a year into the billions. Plus, there's this massive physical balancing act going on. Optoelectronic devices are cramming hot electrical processing and highly sensitive optical systems into incredibly tight proximity on the same chip. Traditional electronics just naturally generate massive amounts of heat, and that heat can severely disrupt the delicate performance of the photonics. So managing this thermal conflict within these microscopic spaces remains a constant, everyday engineering battle.
Let's wrap things up with Section 5. The future of light, from AI to quantum.
This technology is reaching way, way beyond basic telecommunications now. In high-performance computing, it's becoming the critical tech to relieve data bottlenecks for intense workloads. We're talking AI, running digital twins, and even Bitcoin mining. Over in healthcare, new photonic sensors can measure microscopic changes in a sample's refractive index to identify specific disease biomarkers. In the automotive world, it's enabling LiDAR systems for self-driving cars that are vastly smaller and more power efficient. And in the bleeding-edge realm of quantum computing, Silicon Photonics provides a fast, cheap, and highly accurate way to manage the light that carries quantum calculations.
So what does this all mean for us? Well, it brings us to a final, pretty provocative question. We've seen how this precise engineering is paving the way for the absolute next generation of microchips. But as artificial intelligence and quantum computing continue to demand effectively infinite bandwidth, will light ultimately replace the electron entirely in our processing systems? It is a massive hardware revolution happening right beneath our noses, one microscopic laser at a time. Thank you so much for joining me for this explainer.